Hello everyone. Today we will discuss about an important device called transformer. So transformer is a very important device. We all know that the power is transmitted to long distances at high voltage. So wherever the power stations are there, that voltage is to be converted into high voltage, and whenever for domestic use when we need it, we need to convert it back into a lower voltage. So this function, low voltage to high voltage and high voltage to low voltage, is performed by a device called transformer, right? So what is transformer? It is a device which converts low voltage alternating current. This is important. I'll explain why. To high voltage alternating current and vice versa. Vice versa means it can convert high voltage also into low voltage. So why it works on AC only, not on DC? Because of the principles. I'll explain it after the principle. So what is the principle of a transformer? It works on the principle of mutual induction. Which states that when a flux linked with a coil changes, it produces a current in the neighboring coil. So this we have discussed in detail in the previous chapter. So if this is based on this principle, so flux will change in case of AC throughout, because the value of AC current is changing with time every moment. But DC, in case of DC, only the key inserting and key removing part, there is a change in flux. So whenever there is a change in flux in one coil, then it induces a current in the neighboring coil. So this is the mutual induction case. So it does not work for DC. As DC current is constant, right? Now let's move on to the types of construction of transformer. But before that, we will discuss types of transformer. As I told you that sometimes we need to increase the voltage and sometimes we need to decrease the voltage. So based on this is of two types: step up transformer, so which converts low AC voltage to high AC voltage. And here step down transformer, it converts high AC voltage to low AC voltage. Now we come to the construction. This construction is of two types. One is core type and the second is shell type. I'll draw this diagram for step up transformer and I'll tell you how to draw it for step down, because sometimes the question is separately asked that draw it for step up or step down. So if I'm drawing it for step up, in step up, number of turns in secondary is greater than number of turns in primary. Okay, so in core type, what are we doing? In core type, we are having a core of transformer like this, and this is the primary which is connected to the mains supply, that means AC input, and the other coil is connected to the load, or you can say the AC output. In this case, you can see that here NS is greater than NP. So this is step up transformer, right? And second diagram I'll draw for shell type. In shell type, we have this is AC input or mains, this is load, or you can say the output. So this is your shell type. In this case also number of turns in secondary is more, so we can say that this is step up. In case I would have drawn here less number of turns, then this would have been step down. Here in this case also the same thing applies here. Then we have its working. Working, as we know that when flux linked with primary, let me mark the input as primary, and this side is coil is called as secondary. Similarly here this is primary and this is secondary. So when flux linked with primary coil, changes, it induces current in the secondary, right? And here a back EMF will be generated. So EP is equal to minus N d phi by dt. And if I am writing for primary, this would be the number of turns in primary. I would have written this P suffix here, but I'll remove it later on. I'll tell you why. Similarly, for secondary, I can write number of turns in secondary d phi s upon dt. But we consider that there is no flux leakage, so the input flux is totally transferred to the secondary. For no leakage, of flux, d phi p by dt is equal to d phi s by dt is equal to d phi by dt. So we will write it simply minus n p d phi by dt, and this will be minus n s d phi by dt. This is ES, right? And also EP will also be equal to voltage across primary, and ES will also be equal to voltage across secondary. I take this equation as 1 and this equation as 2. So 2 divided by 1 will give me ES upon EP is equal to minus NS d phi by dt upon minus NP d phi by dt, and this will also be equal to Vs upon Vp. So this will be cancelled, this will be cancelled. So you can write down Es upon Ep is equal to Ns upon Np is equal to Vs upon Vp. So this is one important relation, and we consider an ideal case where power input, so input power is equal to output power. So this will be Vs Is is equal to Vp Ip. So from here Vs upon Vp is equal to Ip upon Is. This is your equation 2. So from 1 and 2, Es upon Ep is equal to Ns upon Np is equal to Vs upon Vp is equal to Ip upon Is. Inverse proportionality. So this is an important result which tells us that the transformer does not violate the law of conservation of energy. Why? Because when voltage is high, the current is low, and when current is high, the voltage is low. So when voltage is high, current is low. When current is high, voltage is low. Therefore, transformer follows law of conservation of energy. Okay, so this was all about the basic concept of transformer. Now we have to discuss the efficiency and the energy losses, so which we will discuss on the next slide. Now we come to the efficiency of a transformer. Which is denoted by eta. Now this efficiency is written by power output upon power input, and if we are writing, this will be Vs Is upon Vp Ip, and this can also be written in percentage form like this. So Vs Is upon Vp Ip into 100, right? So practically efficiency of a transformer is less than 99% due to some losses in the transformer. So sources of losses in a transformer we'll discuss here. So one is eddy currents loss. You know that eddy currents result in loss of energy in the form of heat. In the core, heat generated in the core of the transformer. So this can be solved by taking laminated core. What is the solution? Laminated soft iron core. Why soft iron? We'll discuss in the second point. Second is hysteresis loss. So hysteresis loss is the loss of energy during the magnetization and demagnetization of a magnetic material. The loss of energy due to magnetization and demagnetization of magnetic material. Now this can be minimized by taking a material whose hysteresis loss is less, and soft iron is such material. You have already studied in chapter 5 that this hysteresis loss is measured by the area enclosed by the hysteresis loop. So less is the area enclosed by the hysteresis loop, less is the loss of energy. So for soft iron, the hysteresis loop is of less area, that's why we are using this. Now third is your flux leakage. So flux leakage can be reduced. Flux leakage means the whole of the flux produced across secondary must pass to the produced across primary must pass to the secondary. So flux, this is the solution is winding one coil over the other. And fourth and the last loss of transformer is considered copper losses or winding losses. Copper winding losses, because we know that in an inductor the winding is of copper wire. So ideally we consider that inductor has no resistance, but due to this copper winding there will be some resistance. So this, which will result in the loss of energy in the form of heat. So the resistance of the copper winding results in loss of heat, right? So therefore this is reduced by taking thick copper winding. Solution is thick copper wire for winding reduces heat loss due to resistance. Why so? Because resistance is inversely proportional to area. If it is thick, the resistance will be less. So that's all for now about the transformer. Hope you understood everything. That's all for now. Have a great day.